everyone, and thank you for joining. My name is Amekamba, and today we'll be discussing system design, observabilities, production readiness. Uh, as system grows, writing code is no longer enough. We need to design system that can scale, survive failures, and be understood in production. And today's session focuses on how real-world systems are built and operated. So for the agenda, by the end of this session, you should understand how modern systems are designed to scale, or we will explore microservices, event-driven systems, caching, loading, load balancing. We'll also look at observabilities and how engineers understand what's happening in production. And the goal is to help you move from writing code to thinking about the systems. So why system design matters? As application grow, complexity increases, and more users, more data, more services introduce new challenges. If the system is poorly designed and performance drops, debugging becomes difficult and outages become frequent. Good system design to ensure that growth does not break the system. So characteristics of good system are just that a good system is not functional. It's just reliable and maintainable. It should scale as traffic increases and remain stable under pressure. It should also be observable, meaning we can understand what is happening at any point in time. Good systems are designed with production in mind from the beginning. We have monolith versus microservices. So I mean, yeah, most systems start as monoliths because they are simple, easy to build. As the system grows, the monolith can become difficult to scale and maintain. So microservices break the system into smaller independent services. Each approach has trade-offs, and microservices are powerful but introduces complexity. So when do you use microservices? Microservices are not always the right solution for you. They are useful when the system becomes large, when the team grows, and independent development are needed. If used too early, they can create unnecessary complexity. For example, just a team of two and just maybe a simple web application. You don't really need microservices for that. So the key is to introduce microservices when the system actually needs them. Let's talk about microservice architecture. And microservice architecture, each service is responsible for a function. A service communicates with other through API, messaging queues like RabbitMQ or Redis, and this allows the team to scale and deploy services independently. So when you have a microservice, Team A could be working on a feature and a feature service A, and the services are running separately. And Team B is working on maybe the billing system, and the billing system is running on a different microservice. And later, they can all talk to each other. And It also helps to isolate failures. So when you don't want the whole system to fail. So when one service is down, it doesn't affect all the other services. It doesn't bring down the entire system. Communications between microservice, between services, microservices. Yeah, services needs to communicate to function as a system. This can be done using HTTP APIs, like some microservices that you're calling another API endpoint of another microservice. You're using RPC or messaging systems, and each method has trade-offs. Synchronous communication is simpler, while asynchronous messaging improves scalability and resilience. Event-driven architecture. And in event-driven system, services communicate through event instead of direct calls. For example, when a user registers at event, an event is published, like for example, using Laravel, you can just throw user registered event, for example, which multiple services can react to. Usually, like in Redis, like those events are listening, those listeners are listening to the channels on Redis, and they get those events and they react to those events if necessary. So, for example, if the event is for a particular user, and that user is it's just another system, maybe the billing system, that needs to handle that, it takes off and handle that event. This reduces coupling. So the services, they don't really need to know about each other. They don't need to know how to handle those events from another system. They are just listening and they handle it the way they are trained to, they are made to handle those events. And this allows system to scale more easily. Event messaging system. Event messaging system rely on messaging platform like Kafka, RabbitMQ. These systems allow service to publish and consumer event. They act as buffer between services and help handle large volumes of data. Advantages of event-driven system. So the advantage is event-driven system allow system to operate independently, like we mentioned before. New features can be added without modifying existing services. They also improve fault tolerance between services, do not depend on immediate responses. The challenges of distributed systems, the microservices, the challenges. The distributed system include complexity. They introduce complexity, of course, because now you need to start thinking of how to get all the services to talk to each other. Probably you're using Kubernetes for that, and which introduce complexity if compared with monoliths, which just running maybe on a box. Network failures can occur at any time, and data may become inconsistent across microservices, across so many other services. Debugging becomes harder because its issues span multiple systems. Yeah. So, for example, a user registered and you have a microservice where the user register and a microservice that handles sending emails, for example, and yeah, you with the user registered and the email didn't get the other, nobody received an email. So you have to start troubleshooting from the point of did the email even go to the next did the email get stuck in the system, or did it reach the email service? So you need to troubleshoot. It might become more difficult. Debugging, yeah, these challenges must be addressed through careful design. So with a good design, you are likely not going to face these issues. Caching for performance, yeah. Caching improves system performance. Caching is used to improve performance and reduce system load. Instead of recalculating results, we store and reuse them, and this reduces pressure and improve response time. Yeah, there's some, when you introduce caching, your database will be very happy because you're not hitting your database each time. There's some kind of if you're, for example, returning a list of users, for example, you can cache that for the next request. Or on the next request, you're just going to check if the time to leave on the cache have expired, and you could just return that if it hasn't expired. At that point, you return from the cache instead of calling the database over and over again. Common caching layers. Caching can happen at different levels. Application level caching stores frequent access data, like I said earlier. CDN cache, content closer to user, like the pictures and stuff like that. Each layer helps reduce load and improve performance. Caching introduces a challenge, keeping the data fresh. Yeah. If data is outdated, the user may see incorrect information. Designing a good cache strategy involves deciding when to update or expire cached data. Yeah. For example, you're designing a system, you're caching the user profile, for example. So at what point do you invalidate that cache? So the user, I think at the point where the user updates their profile, you invalidate the cache. If there's an existing cache, you delete those ones and recache the updated profile. So having a good caching strategy will help to avoid this issue. Load balancing. Load balancing distributes incoming traffic across multiple servers. This prevents any single server from being overloaded. It also improves availability, and if one server fails, traffic is redirected to other server. Types of load balancing. There are different strategies for distributing traffic. Round robin distributes requests evenly, and least connection send traffic to least busy server. Choosing the right strategy depends on the system requirements. Once systems are live, then we need visibility into how they behave. Observability help us to answer questions about system performance and failures. Without observability, debugging production issue becomes more like a guesswork. You don't really know what is going on. The three pillars of observability. Observability is built on three pillars: logs, metrics. Logs, I mean, like the system, the application need to keep logs. Application need to keep like metrics and tracing. When an error occurs, you need to the application. They're just looking at the dashboard or wherever your logs are going into. You'll be able to figure out where exactly is the issue. Logs provide detailed event data, Metrics provide numerical trends. The metrics are used to measure different aspects of your application, like the way the processing time, how long does it take to calculate, how long does it talk to the database and retrieve information from the database. So tracing shows how requests flows from the system together. They give you a complete picture of what is really going on in your system. Logging logs captured events inside the system. They help diagnose issues after something goes wrong. Structured logging makes it easier to search and analyze logs. So don't just write logs without maybe without keys or information that will help you to filter the log. Your log should be filterable. It should have timestamp. It should have time. It should make it easier. Like if in using the grep in Linux, you should be able to like grep out like a particular date, and you can easily see what's going on. And by some of the levels, you also have different log levels that you can add. For example, the error ones and the maybe information, debugging logs and stuff like that. Metric metric provide real-time insight in system health. They help identify trends like increasing latency or error rates. Dashboard allow team to monitor system performance continuously. Yeah. So we have using things like Prometheus, for example. It helps you to like have different metrics. You have a dashboard you can look at to see trends, what is taking long, request taking long, or maybe an endpoint that needs maybe caching because their endpoint is hit almost every minute or almost every second. So you probably maybe looking at those trends, looking at the metric, you'll be able to know how to improve the system or know what is causing the issues in your system. Why are requests low? Why is the database slow? Probably maybe you need to index the database or something. Just looking at those metrics helps you to know what's going on in your system. Distributed tracing. Tracing helps track requests across multiple services. It should it shows where time is spent and where failure occurs. This is especially important in microservice architecture. It makes troubleshooting in microservice services easier. Observability tools. There are many tools available for observability. We have Prometheus collection metrics. We have Grafana visualize them. With Grafana you can visualize metrics from Prometheus metrics collection. We have ELK stack handle logs for logs, which looks like Jagger. Provide tracing. Those tools help engineer, monitor, and debug system efficiently. Diagnosing production issues. Well, when issue happens in your production, you need to figure it out fast. When issue occurs, engineer follow a process. There should be a process. They check the metric to identify anomalies. They check the system to identify anomalies, and they review the log for detailed information. And finally, tracing help pinpoint where the issue occurred. Production readiness. Before deploying system, we must ensure that they are ready, and monitoring and alert mode is configured, Health check should be in place. System should be able to scale under load. Reliability engineering. So what I mean here is failures are inevitable in distributed system. Reliable systems are designed to handle failure gracefully. Techniques like retries, maybe when a job fails, you have jobs running, you retry, then you can't retry forever. Then that's where timeouts comes in, and circuit breakouts help maintain stability. Takeaways. System design is about planning for growth and failure. Observability is essential for understanding system behavior. Testing and monitoring together ensure system reliability. Engineering is about building system that works under every real-world condition. My final thought, great software is not just functional, it's resilient, it's maintainable. The best engineers design systems that not easy to that are easy to operate, they are easy to monitor and evolve. Just think beyond code. Think about the system as a whole, as an engineer. Thank you very much. I will take your questions now.